Thanks very much, and thank you very much to CEAD for having us on a stand, and thanks Jason for the wave as well. So we've been working with CEAD for a while now, and we've integrated with quite a few of their robots, and yeah, I just want to talk to you a little bit more about the capability what robots can give, how that compares to gantry systems, and go from there. We do have our stand at Hall next as well, so if you want to come across and see us in Hall 11.1 B39, please do that, and obviously feel free to come and see me after the talk and ask any questions at the end of it. So what I wanted to do to start with was talk a little bit where Ai Build have come from. So we started about 7 years ago, and we really were looking at how to solve really large format problems for kind of architectural applications, and really found a problem in the market around what we can do with the hardware and software capabilities at that time. And we really wanted to bring something new to the market when it comes to robots and large format printing. And these are a couple of the examples of our early work. So the part on the left there was a part called the phallus. That's about 3 meters tall and has a 7-kilometer long continuous print bead to print that part. Built over a conformal mandrel, so something which is very hard to do with anything other than a robotic system. The part on the right there is the Daedalus Pavilion, so that's a 5 meter by 5 meter by 5 meter part, and it's an open lattice creation. So this is pulling out the beads into free space, and it only weighs around 200 kilograms. So again, just a different way of doing it from what is available on the market. We then evolved directly into software, and that's the core focus of what Ai Build does, and we rely on key partners like CEAD from the hardware aspect to it. So our focus is on the large format printing and really unlocking the full potential of what 3D printing and robotic systems can do. We've got a little lab facility in London where we have hardware come on site, and that allows us to test out our software in different hardwares. We get an appreciation of what the relevant strengths and weaknesses are, and that gives us an interesting position to be able to give some advice and potentially some ideas about the pros and cons, and we'll go into that in a little bit of time. Obviously you can see we've kind of lent more towards robots, and we'll go into those reasons shortly. So really I broke down the differences between 3-axis systems and robotic systems into these 4 points. The first one is really around the tool paths availability. Typically gantry systems can give you horizontal planar tool paths. This typically requires a lot of redesign work from the CAD design to kind of adhere to the rules, the 45-degree angles and those kind of things. Typically you're also needing to have lots of support, maybe lots of infill as well, which increases the time for prints, time for post-processing, etc. If you compare this to the robotic system, these are some of the examples, and also you can see some parts here which mirror these parts about the kind of tool paths you can do. So if we go from the left to right here, we have the segmented toolpath, which is also shown over here. What this allows us to do is to isolate specific zones of a part, allow us to apply a different parameter set to those, and also allows us to do things like optimizing the toolpath movements. So if you have, let's take a chair with 4 legs coming up from it, on a traditional kind of gantry horizontal printing system, you'd have to do 1 layer of the leg first, jump across to the next one, do that layer, and keep going around. So you have lots of unnecessary moves. With robotic systems, you're able to print the entire leg of one thing first, and then move across to the next one. So you're allowing reduction in the time printing exactly the same part, reducing your stop and starts, and improving the part quality. The top middle part there is the conformal toolpath, so that allows you to print over curved surfaces, allows you to print onto existing parts, which is just something fundamentally you don't tend to have in other systems. So this is really interesting, particularly if you think about linking it to printing onto an existing stock model, and then you just want to modify it on a customer's case-by-case basis. Multiplanar parts, so this part here, this is where you can follow the curvature of a tube, still keeping a flat layer, but be able to twist and move through it. This gives you some benefits, things like tubing, etc., where you can keep consistent wall thickness, and that allows you to improve things like air tightness, water flow, and things which improve the quality of the pipes, for example. And then the final part there, non-planar, so being able to move through X, Y, and Z as you're printing. Quite interesting applications when you think about stresses going through parts. So FDM, FDF processes, typically your strength is through the bead rather than through the layers in between it. So if you can then guide your tool path to follow the maximum stresses through the part, you can actually have a higher performing part coming out of it comparatively to a part which has just been sliced horizontally. The next thing we're kind of talking about is a little bit more around the actual structural makeup of the robots themselves. So typically the gantry systems are a little bit more fixed in their envelope. What that gives you is if you want to go outside the 1 minute or 1 way, 1 meter build envelope, for example, it's quite hard to do that. You typically can't modify those machines, you can't negotiate them, so you tend to have to move towards a bigger machine or buy a bigger machine. With the robots, not only are their build envelopes a little bit more fluid, they've got a bigger envelope along those lines, but you can modify them. So you can put them on a plinth, as you can see over here, which will increase your Z-axis. You can add a linear rail, you can add an external positional system, and your original purchase of the robot system is actually still relevant and useful into what you've got there. So it gives you something additional to do from a modification point of view. So really just an increase of flexibility. They're also designed robots for a lot of different tasks in there, so interchanging between from printing to machining to pick and place and all those kind of things. There's a lot of capability which goes into that. And finally, there's the price point. We know that robotic systems typically cost somewhere in the region of 200 to 300,000 euros, and gantry systems of around 2 meters plus in size will be setting you back anything from between $500,000 to 2 million euros from that kind of thing. So really you can get a lot more for less money along those lines. So just to give an example of some of the tool parts in action. So this is all printed in our lab on the CEAD systems, and you can see the kind of angles the heads are going to be going to, particularly in this middle one, and you just can't push it that far on a gantry system. You can do some of these tool parts to a point on a gantry, but really getting that full movement, that full flexibility is just something only robot systems are going to be able to give you. So really, in summary, for me, the price comparison between gantries to robotic systems is a big telling factor. It's the greater capability of how far you can push those tool paths, and it's the flexibilities the robots give you as a combined whole, which is really the benefit from it. And just to finish off, I just thought I'd share a case study example which we use the CEAD extruders for. So this is a company called Weir. They're an oil and gas company making pumps for the oil and gas industry. And this is a sand casting pattern. So what this is, if people don't know about sand casting, you put the pattern into the mould, you cover it with sand, you pack it down, you turn it over, you remove the pattern from it, and then you fill that cavity with molten metal to create your part. This was something which was taking them 6 weeks to do from traditional manufacturing. With the robotic systems, it's down to less than a week through there. It's about an 80% reduction in cost, and really the weight aspect was the particular interesting thing. So this was the first iteration of it, and this was actually printed with infill all the way through the part. So typically horizontal slicing, lots of infill, quite a lot of weight. The next iteration we did, you can see from the toolpath up there, we removed all the internal infill from it, and using the additional flexibility that the robot system gave us, we were able to cap across that, and that allowed us to take 40 kilograms, about a third of the weight of the part, out of it by removing the need for the infill, and that obviously reduced the time to build that part by about 30% as well. So that was really a great use case to show where the robotics flexibility and the capability those degrees of freedom give us allows us to actually reduce the weight comparatively to a similar part printed on a gantry system. So yeah, that's everything from me. As I said, we're in Hall 11.1, B39, if you'd like to come and see us. And obviously, any questions or anything on those lines, please ask and come up and talk now. Thanks.